So my name is Victor Moreno. I have been working for a very long time on trying to simplify networks, and in that quest I've worked on a bunch of different technologies. I've partnered with Dino, who is going to be on stage right after the break, on developing and bringing to market a series of different technologies, and one of them happens to be LISP, and probably the most promising one that we've worked on in the last 20 years. So in that process of working on LISP, part of what we do is we standardize what we do, because we want this to be open. We want everybody to be able to actually tap into the technology and get the benefits and really move the internet to its next stage. In the process of standardization, we ended up in London about 6 months ago, and Dino shows up with Colin. I had no idea what Colin did, who Colin was, and he introduces me to Colin, and Colin, of course, within 5 minutes starts telling me all about mathematics and cryptography, and it just goes way over my head, and Dino sees my glazed look. He's like, well, you should read our document. And the document that they've written and they brought to the standards body was called LISP Decent. And I'm like, well, yeah, Colin looks like a very decent guy. I mean, this is okay. Well, why this document, and what is it about? Well, decent actually is not about decency, it's about decentralization. I'm like, okay, cool. So they wanted to decentralize the control plane that we were using. They wanted to take the LISP system and take that single point of control and decentralize it. And I'm like, well, that sounds interesting. Why would you want to do that? Well, I need to run a blockchain on top of this. I'm like, oh, but now I'm really confused. You're a decent guy, but you print money. So where are we? How are we going to go on about this? I'm like, I put my trust in Dino. I was like, okay, let me get to know Colin a little bit more, and we start talking, and he actually walks me through all the wonderful things that we can do with this blockchain. And after a few drinks, and everything in LISP happens at the bar, but after a few drinks, and a lot of really interesting conversation, I had my moment of serendipity. And I love that picture of that meditating dog that Carolyn put up there. But after that, all I could say is, where do I sign? How do I help? And here I am basically to do my little bit and give you guys an introduction to general networking and what we do in LISP to actually decentralize networking. So the question is, why do you need the network, and why is LISP important to you? And the key thing, if nothing else, if all the technical stuff that I'm about to go into doesn't stick, the key thing is that we need mechanisms to evolve the internet to provide services that support the blockchain, and we need those to be independent of the intermediaries. Right now, the network is basically a very granular operation where you have to control all nodes between the parties that are communicating. So we want to decentralize that, and we want to take that intermediary out of that control point. But we also want to bring services that are relevant to the blockchain, which those intermediaries may or may not have an interest in providing and delivering. Okay? So that's the key thing, the key reason why we want to do what we want to do in networking. And in order to optimize the application, it's critical that we actually do look at the full stack all the way from the application to the ground level where we're actually providing the connections. Right? We see many applications that are unsuccessful at scaling. Our own applications at Cisco, where we have controllers for our systems, where due to lack of good integration with the network and the I/O mechanisms, we're not able to actually get the performance that we need out of the systems. So how do we do that? What is this whole thing about LISP? It's not a speech impediment. It's not an old programming language either. It's basically the name we found to capture the essence of what we're trying to do. We're trying to separate the two semantics that exist in networking addressing, which are location and identity. So if I talk to my mom connects to Google. She connects to Facebook, Instagram, and she doesn't know that it's being filtered, as Nick shared with us. But she sees this as this magical cable that connects to this ethereal thing, and in her mind, she connects to names. Well, it turns out computers don't speak names, and the network especially doesn't speak names. The network speaks addresses. And those addresses today basically contain both the identity of the endpoint that we're connecting to, as well as where that endpoint may be. And mangling this together has led to basically all sorts of complications in the network. Complications that actually preclude certain behaviors in the applications that are required in modern times. So when you get your computer connected here in this building, you are going to be assigned an IP address, and that's what the network is going to use to get information back to your computer. That's what the network is going to use to source information from your computer. And as you move to your offices or the airport or wherever you may go, you're going to get a new address. And the application is going to now be pressed to recourse to all sorts of other mechanisms to understand that your address has changed, the connections need to get reset, and if you were hoping to actually attach any sort of hash mechanisms to those addresses, well, you're out of luck, because the address is going to change every time we go around. Now, in between these 2 points, and as we get information from one place to the other, this granular information on addressing needs to be spread across the entire network. And it's not a magical cloud. It's basically something that, if I was to try and simplify what the internet looks like, you can think of it as a fishing net. And a fishing net that has much intelligence in every one of the nodes where the threads are actually being joined one to the other. At each one of those nodes, a decision must be made on how to best get to that address that we're looking for, right? So you have to inform every node, everywhere in that network, of where this 20 address or this 10 address are actually at. And if things move, you have now a massive reconvergence event. And if you think about it at the scale of the internet, basically what the internet has done, it has masked a lot of this by not allowing mobility and by not giving you the granularity of tracking where every endpoint is at. Okay, so those are the things that need to evolve. So what did we do? Well, we basically said we can keep the addresses of the endpoints fixed. So your miners, your wallets, your phones, they will have a fixed address, and then all we need to do is build that fishing net amongst the devices that we connect to. So as you go home, basically your home router would actually be connecting to this fishing net, and that's where all that reachability will be achieved, right? So you end up with a pretty static core that is this fishing net where you can actually get between the red addresses, between 1111 and 2222, okay? And then all we're going to do is we're going to create a database where we map basically our endpoints, wherever they may land. We're going to map them to their attachment points in this net. So the net becomes immutable, and now we're solving a problem that is much different from the problem we need to solve in that net, which is a problem of multiple paths and reachability, availability. We're no longer solving for that. All we're saying is, did I attach at 1 or did I attach at 2? And my persona remains constant. So I've separated my identity from the location. The location is the business of the routing protocols and the internet as you know it today. That works, and it works really well. Now we want services that are pertinent to the endpoints, and we separate the endpoints from that core. Okay? So the task that LISP achieves is basically mapping and remapping those identities to different points of attachment in the network. One way of looking at it is we have our existing network, and we talk about that as the underlay network. That is our fishing net. In that fishing net, we're going to run protocols that run all sorts of path computation and are rather sophisticated and fine-tuned to do things. This is where we're at right now with networking. Very resilient, very reliable. We can actually get connectivity amongst all of these devices. But we want independence from the intermediaries that are actually running this. We want to decentralize this. So what do? We basically put intelligence at the edges of that network and create virtual networks that simply leverage the services that are in that fishing net. So we create what we call overlay networks. These are virtual networks that are now under your control. Understand that these edge devices may be in the form of just an application shim inside of your wallet, inside of your miners. So now I can create basically a virtual network experience starting at my very computer and go over the top of all of this. So the intermediary is simply providing a packet forwarding service. Meanwhile, all the intelligence on how I'm going to replicate traffic, if I'm going to encrypt it, what kind of connectivities I'm going to have, the preservation of my IP addresses is all under my control. But it doesn't have to be centralized. That's where the decency in the document that Colin and Dino proposed comes in. We can actually make that decentralized. So think of the network as the underlay. That is your phishing net, and then we're going to create overlay networks. Those overlay networks are going to have their own control plane, which is a much different control plane from the one you have at the phishing net level, at the underlay level. It's a control plane that is simply a mapping database that keeps track of locations and where those, which locations the identities are actually attached to. So from the perspective of your application is basically connecting to this virtual network. And now we have the liberty of implementing all sorts of services that the intermediary that's running the underlay network may or may not provide. Now, one key concept to this is we're going to encapsulate the traffic. And what we mean by that is we're going to limit the forwarding task in that underlay network to basically getting from one edge device to another edge device, regardless and in ignoring the fact that I may be connecting from computer A to computer B. I'm going to be more concerned about getting from attachment point, ingress attachment point to egress attachment point. So if you think of it as a little ant running through that phishing net and having some notion or some level of intelligence where the ant can check at every node of the phishing net where it needs to go next, that's what the ant is going to be handling at the underlay level. That ant is going to carry a breadcrumb, and that's basically our message for our blockchain, right? The ant doesn't know what's in the breadcrumb. The ant doesn't even know that the breadcrumb is destined to one or more nodes. She doesn't need to know. The ant only checks in the phishing net, okay, where do I go next? Do I go left? Do I go right? Okay. Take a taxi driver, for example. He would be instructed to take you to the doorstep of an office building. He doesn't know which room and which person you're actually meeting with. He doesn't know you either, right? Your payload, your opaque payload, you're encapsulated. So this is the foundation of what we're doing. Now, in order to do this, we have to use a different paradigm in the control plane layer that we have in the overlay. We can't just use the routing protocols that we have traditionally used. So we choose to use a demand-based protocol because all we're handling is mapping and an update of a database, right? It looks very much like what we do in the domain name system. In the domain name system, basically what happens is you look at for the IP addresses that correspond to the names you're trying to connect to. So for my mom, when she goes to Instagram, she doesn't know that she's connecting to an IP address. She doesn't know her computer speaks IP. Yesterday, there was a comment made that very few people understand TCP/IP, and I don't think people need to understand TCP/IP as long as Dino is not retired. So basically, you request the IP address where a particular application is being serviced. You're looking for the location of that application. And today, that location is co-joint with the identity of the network node that is actually running the application. And what you get back from that query is basically an IP address. By means of introduction, I've kept here some rather complicated semantic of IP addresses where you have the first one is basically 4 numbers, 153.16.529. That's an IPv4 address. And if you've heard about the world going to IPv6 because it's going to, we need more addresses, basically that's the address that you see on the right-hand side. So you can reach that service using either one of these addresses. And the network, the underlying network, should know all about it. Now, if we want to take those addresses out of our underlying network and provide services based around those identities, well, basically what we do is we take those addresses and we do a very similar lookup in LISP. So our overlay control plane is basically looking for where are these endpoints attached in the network? Are they at the hotel? Are they at home? Where are they, right? And we get back some more addresses, right, for that ant to actually get from point A to point B, for our Uber driver to be able to drop us in the right place. So we're using a demand-based mechanism. And the key reason why is for us to be able to actually scale things. We can't scale to the levels that we need to scale if we keep doing what the internet does today, which is basically, I got a bit of information, I need to tell everybody in the world what's going on. We just need to tell the interested parties. The interested parties are those where communication is established, right? So similar to DNS on your computer, if you went through a bunch of websites, that's what's going to be cached on your computer. You're not going to have a cache of absolutely everything that exists in the internet, right? Your computer would never do that. Same thing with the networking stack, the evolved networking stack for us to enable these services. So the way our request and reply mechanism works is interesting because there is a central repository, which we're working on decentralizing, but there is a central repository that actually refers or contains information on where everybody's attached. In this example, X is attached to 3, and Y is attached to router N, right? So our little ant just needs to know to go from N to 3. And that is actually in our database. And you could argue that that database looks like a central point, but Dino and Colin will show you demos on how we've actually decentralized even that. And your request will go through that, but it's a referral system that actually takes you all the way to the edge device where you're connected. So the request actually goes all the way to 3, and then 3 replies, and you get your mapping, and you're going to cache your mapping. So now element N knows how to get to X. So he can tell the ant, listen, I have a packet for X, you don't care about that, just send this packet over, carry it over to 3, and 3 basically is well known within that underlay network. Okay? So that's our system in a nutshell. You encapsulate the data at that point and you send it straight through. So we've created a virtual network on top of the existing internet. And when I say internet, I'm referring very loosely to the combination of the public internet, your private networks in different companies and enterprises, and whatever you have provided by the cellular providers. So what is the implication on applications? Right? So we can offer services that are not available on the internet today, and it would be very difficult for the internet community to reach an agreement on how to deliver. One of the key ones is mobility with IP persistence. And this is something that the 5G development groups are struggling with on how they actually do this at scale. We're talking massive scale, everything connected, plus some more, billions of endpoints. And because it's mobile, it's now granular to the level of the host. So there's no more summarizing, well, if you want to get to something that's owned by Google, you're just going to send it to one big fat Google address, and then they will actually disseminate it at that point. No, things are moving all over the place, and now you have to have that presence everywhere. So we need to do this at very large scale. We want cryptography for a lot of this. So we want to provide as many layers of encryption as we can. And in the case of the blockchain, we want basically the ability to encrypt our traffic in flight. So when we have a transaction and we're actually disseminating the information for that transaction, we want that to be encrypted as well. How do we do that in a scalable way, in a decentralized way, and establish pairwise relationships? Very important, and one thing that you will see in the demos after the break, multicast services. This allows us to basically reduce the amount of signaling that a node may need to generate to actually initiate a consensus transaction. And IP address privacy gives us the opportunity to look into using our IP addresses as part of our hash and as part of our consensus algorithms. So when you talk about privacy, basically what I'm saying is those identities that are registered with the mapping system, with our LISP system, aren't necessarily available in the broad internet. So I can actually create a private space, make it reachable, and when you look at the guy on your right, he is going to basically have information on how to get to all those red prefixes, N, 1, 2, 3, 4. He can get everywhere. He doesn't have any information on how to get to A, B, C, D, which are basically your mining nodes and so forth, and doesn't need to. But everybody in the blockchain can actually get to each other. So this has profound implications on how we can actually leverage that network identity in our hashing. Now, the other interesting thing is mobility at high scale. So we talked about how we actually obtain our mappings. Well, when something moves, our mappings need to be updated. So before I move, I'm sending traffic for X. I'm sending that traffic to node number 1. And now X moves along, and that's my poor attempt at getting an animation going. And then he shows up at site number 2, and at site number 2, he basically needs the ant to take things to a different place. Now, we need to tell that ingress point where to send traffic to. We need to actually update that, and the way we do it is we basically detect the moves dynamically, and we use our mapping system to actually funnel signaling back to that ingress point. And that ingress point now knows how to get things down to number 2. So this may seem obvious, but you would be surprised how many smart people in networking look at this problem as, oh, if you want to change location, I'm going to tell everybody in the world, and it's going to take about 10 minutes to update the internet so that we know that you've moved to 2. So we need to be very prescriptive on how we actually insert this information. And that's part of what we do with Lisp. That's part of what you will see in the integration of what we're doing with the blockchain and the Lisp technology. Once you've updated that map cache, you're now sending traffic to the right places. Okay? So the key here is that X didn't change as I moved from left to right. Okay? X remained the same IP address, so now my application didn't actually have to reconnect, didn't have a reset. It's basically giving me a seamless environment where it doesn't matter if I'm moving or not moving. It doesn't matter if I'm changing locations or not changing locations. Whatever I've done that is anchored on that persona, on that identity, it will be persistent along with the identity. The other part that's interesting is we talked about our map request and map reply, basically our resolution mechanism actually traveling all the way to the egress points in the network, right? The benefit of having this integrated or having the signaling go all the way between the ingress point and the egress point of the network is that we can now exchange public key material in that messaging. And we can run a pairwise Diffie-Hellman exchange between these and come up with shared secrets. We have basically defined a list of 6 different cryptography suites that can be used in this system, but basically the key here is that now for every different connection I can have different crypto keys selected. And we have all the mechanisms to actually rotate those keys in our encryption header and calculate them offline and be very efficient in how you create a widely distributed encrypted infrastructure, encrypted network infrastructure. So now when you have a transaction and you're going to basically send that all over to your miners, well, guess what? It can also be encrypted. So you have that extra level of security so that can't be tampered. And that brings me to the key performance enabler that we are exploring with Colin, which is basically the ability to handle multicast. Now, when you think of what we're trying to do here at Nexus, which is basically put miners in space, have some on Earth, have your wallets actually be able to do proof of stake, and have this very high density of interested parties, we need efficient ways of doing things. We can't have the node in the nanosatellite have to send 1 million copies out of the information that it needs to send out. So what do we use? We use a mechanism called multicasting. And in multicasting, what we do is we try and reduce the amount of copies of information that is destined to multiple interested parties. So if I think of the network as a series of strata, I will send a single copy until I absolutely have to duplicate or replicate the information until I get everybody covered. So in this example, right? I'm going to send a copy to a node 4, and there's only one listener on node 4, so I just deliver my information there. But I also send a copy to node 1, because behind node 1, or I'm using node 1 as a proxy to replicate traffic to nodes 1.1 and 1.2. So you can see how my nanosatellite only generated 2 packets, rather than generating 1, 2, 3, 4 packets for this replication to occur. Now, if you take that at large scale and you create a mesh network, you can see how I can have the satellites that are contiguous to each other start hearing from each other and optimize things. There's nothing that the intermediary network has had to do different at this point. Now, if there are portions of the network that I own, I can then run multicast in those portions of the network that I own natively. So there's traditional protocols that actually create these distribution trees dynamically. I can leverage that as well. And I can use a combination of what we call over-the-top multicast, which is strictly overlay-based, and some underlay service that may or may not be available for us. Okay? The key here is that I've reduced what would have been 1, 2, 3, 6 messages. I've reduced to basically 3 messages that come out of my node. And you can extrapolate how in a very large network this becomes a big deal very quickly. The key is my I/O on my node has now actually freed a lot of cycles for me to actually do things in a better way. Okay. So capacity is key. So these are the very high level aspects that we've looked at in terms of optimizing the network for the blockchain. And they need to be integrated to each other. So IP address privacy, the confidentiality and encryption of the connections, and the optimization of the distribution of the data, right? All coupled with high scale mobility. We're in a world of mobility. A lot of what we see is in the realm of connected vehicles, connected drones, civil aviation, very high scale, everything connected, things moving at scales that we haven't seen before. So I'm not sure if I did justice to the consideration on demand-based protocols being critical to achieving those scales. But more than happy to talk more about it as we progress through the conference. So as far as standardization and openness, we've, well, especially Dino made a point early on not allowing this to fall under the control of an intermediary, which would have been a networking vendor making a lot of money out of this. We took this to the engineering task force. He prohibited, he banned us from, he was senior to all of us, by the way, that's how you can ban, right? So we talk about decentralization. He actually put a very serious guideline on not patenting anything that we were doing. Everything was to be put in an internet draft and offered to the community. Everything was to be shared with the open community. A ton of open implementations came about. So in the last 10 years, we basically worked from a research group that was suggested in Amsterdam back in 2006, I believe. And that research group was tasked with basically simplifying the problem of the bloat of the internet routers because they were getting too many addresses. And that's where we thought, we'll separate location from identity, let those routers only handle location. The identity will be handled out of band, right? So that's how the internet routers that were about to burst at the seams were actually allowed to keep pace.
Come see what we're doing at nexusearth.com.